Okay, the next speaker is Gonda Brunton from Lawrence Livermore National Library. Gonda is the National Ignition Facility Control System lead with 24 years experience in large-scale distributed control system design and implementation. He has been with the Lawrence Livermore National Library Laser Project for 13 years with position held in the development of Canada air traffic control system and military message handling system. Okay, welcome, Gonda.
Thanks, Shimping. Good morning, everyone. So I'd like to give a little bit of an introduction for, we've presented at ICALEPCS many times before, but the National Ignition Facility is the world's largest operational control system. It's very large scale, data driven, very distributed, over 2,000 remote processors within our facility, and very automated. All our shot sequences are vastly automated to allow us to be able to get enough shots off per year. Our major focus in the past couple of years since we last presented at ICALEPCS has been on increasing our shot rate on the facility, as well as continuing to add more diagnostic capabilities. And we've had a particular focus on sustainability of our control system to make sure it's fully maintainable for the next 20 years of operation. It's been operational since 2009. So at the last ICALEPCS, I spoke about efforts we were doing for the systems engineering and trying to improve our shot rate. We set ourselves two very large goals in FY15, 300 shots, FY16 of 400 shots. We did this primarily in three major focus areas. One was to increase the amount of shot time. We increased the number of shots on the facility from 40 weeks per year to 44 weeks. We improved the experimental scheduling by reducing the amount of diagnostic reconfigurations that we had to perform in between each of the shots. And we had a very focused effort on advancing the automation in the system to reduce the shot cycle durations. As you can see from the chart on the right, we surpassed our goals, both in 15 here and in 16. And we're kind of showing, as of the 27th of this month, which is really close to the end of our fiscal year, we've shown that that kind of rate is sustainable kind of going forward. And this allows us to provide more shot opportunities for all of our mission spaces that the facility supports. One of those mission spaces is the Inertial Confinement Fusion, or ICF. We've had a lot of really good results recently. In the past couple of months, we had our first 1E10 to the 16 neutron yield from our DT targets. In the past couple of weeks, we surpassed that even further, but it's too new that I couldn't put it on the slides. And we want to continue advancing this. I mean, one of the goals of the facility is to get ignition through fusion, but we only have one positioner on our system that is capable of doing the layered DT targets that are used by the ICF program. And it would impact shot rate if we were to dedicate more time to that. So we recognized this a couple of years ago, and we decided to invest in building a couple of new positioners, the tandems. And we decided to make them dual function, both as to be used as a diagnostic alignment positioner or a target positioner. So this year we commissioned the first one. Here's the picture that it's setting up for a target experiment. And then we expect to have the second one, which will be predominantly for diagnostic alignments, operational by the end of the next fiscal year. This allows us to interleave non-layered target shots on the new tandem as well as the non-layering positioner, whilst also allowing continued accelerated advancement in ICF. Coupled with the tandems, we've decided to implement a new alignment strategy. This is the Advanced Tracking Laser Alignment System, or ATLAS. The picture of it here in the top right. It's a commercial off-the-shelf laser tracker. What it does is it sends in a laser beam into retroreflectors mounted on each of the diagnostic payloads. And then through a series of data acquisitions and integration of all that data, we can calculate a 6-dimensional position and orientation of that payload at the end of the positioner. And we use this in a feedback loop coupled with a semi-automated alignment process to actually align each of the diagnostic payloads. And then this replaces the existing system. This is a kind of a graphic showing the field of view, the new Atlas system. It covers the majority of the chamber, as opposed to the previous system, the post-port alignment system, which we were required one system for each positioner, and that eliminates this overhead having all these additional systems, because this one system can align all of them. So I'd like to make a special call out. We've got a couple of presentations during this eclipse, one from Rick Wilson, which will be going into more detail on the Atlas system, a bit more technical kind of detail, and then also Mikhail Fedorov, who will be giving an overview of the semi-automatic alignment process and the strategy that we use for that. So far, the it's been commissioned for operational use, and the results have been very positive. We are able to align all our tolerance, all our payloads into 0.5 millimeter alignment tolerance, which is well within specification. We obviously invested a lot in lots of automation. I wanted to make out one special sort of call out of an area that we focused on that had a great benefit. Most of our diagnostic reconfigurations we perform in field requires manual intervention, going out into field, breaking sweeps, etc., and take a lot of time. So as part of the shot automation, we identified which ones had the biggest bang for the buck, and so we implemented a lot of automation for remote attenuator and filter wheel control, which allows all these reconfigurations and removes human error remotely. And it was certainly a large contributor to us improving our shot rates. Small program update. I've spoken before at Eclipse about one of the particular large-scale diagnostics we added for the Advanced Radiographic Capability, or ARC. This is a petawatt 1 omega short pulse laser system that's used for multi-frame X-ray radiography. It allows us to image ultra-dense targets at bang time a lot better than any other diagnostic capability that we have. However, it is a very complex control. It adds about 60% more additional control points versus a NIF beamline. And in the past, since the last report, we had issues with meeting the requirements for particularly pre-pulse requirements, so we ended up having to replace the entire front end that was fiber-based before with a completely new high-contrast free-space laser. That has now been deployed, it's been fully commissioned, and we're starting to get our first data, as kind of shown here. Very complex target setups, but is a very key diagnostic to our high energy density physics experimentation. And we are currently fully commissioning it in conjunction with the platforms, and we expect it to be available by next fiscal year. In support of the ICF program, one of the areas that we are exploring is the symmetry of the target implosions, and we were lacking the diagnostic capability from various angles. So we chose to implement a new diagnostic that has quite different capabilities from our traditional ones. So this real-time neutron activation detector, RTNAD, deploys 48 symmetrical detectors around the target, and at bang time the neutrons that are emitted from the target implosion are then captured in a zirconium crystal that is in each of these detectors. And through the DigiBase detector on the end of it, it measures the emission of those neutrons from the zirconium over the next several hours. I mean, in the accelerator community, I know that we're kind of talking terabytes, but 20 gigabytes of data for NIF is actually quite a large amount of data set. So we use a CoreSight Pi interface to integrate all this data and then do post-processing on it that then allows us to see the symmetry from 48 various lines of sight to help us understand how the symmetry of the targets is actually performing, and allows us to adjust. And it's one of the elements that we're using to finesse the experimental setup to help us improve on our ICS experimentation. Sustainability is a key focus over the past couple of years. It's important to us that we are capable of supporting the control system for the next 20 years. So we're investing both in software and infrastructure and processes to make that happen. I've spoken before that we originally wrote our product in the Ada language, and it's kind of difficult to get Ada engineers. In fact, it was difficult 10 years ago to get Ada engineers. So we've been in this multi-year port phase, and we have about 80% of the control software now ported over from Ada to Java, with about 70% of the 2,000 control processes also converted. We mandated at the time of starting the development that we would mandate the production of a unit and integration test suite for each of the devices, which is integrated into a continuous build process. This was important both obviously to keep the availability high in a 24/7 operational facility, but also allows us to kind of document the expected system behavior so that when we get onboarding new employees, which is inevitable over the next 20 years, that we actually give them a basis on which they feel comfortable making change and minimize the amount of bugs that kind of creep in over time. And like Tango, we are kind of based on a Corba middleware, and this has been very effective in supporting a phased delivery of these upgrades out to the facility. And then we also have another talk. Barry Fischler is going to be talking about lessons learned that we've kind of gained through this process and how we've refined it through the years. We expect the full commissioning to be complete by the end of next calendar year. As we've been operational since 2009, there's a lot of data that we have that we can do lessons learned on, both from a log file perspective as well as configuration, archive. And we've been trying to leverage this to do some analytics. We've been using a product called Splunk. We've spoken about it before. We have another presentation in this Eclipse on further use cases. And this allows us to aggregate kind of various different pieces of data in order to extract information that we use for various process enhancements. A couple of the examples that we use this for, the picture here is of a multi-level Gantt chart that's extracted from the timeline of a shot cycle that allows us to drill down to various levels of detail to help us look for optimizations in our process. We've also used it for predictive analysis on our amplifier capacitor failures. Looking for a particular signature that we identify, we can do multi-year analysis and prediction on that. And we also use it for real-time alerting for kind of off-normals, key performance indicators on the control systems. The various members get real-time notifications to try and intervene before they become problems. So if you want more details, Mike's got a great talk on that. And we're still continuing to expand our capabilities. There's various large-scale focuses in the next year. We're focused on this new optical Thomson scattering diagnostic. It's a 1 joule 5 omega UV probe beam that's going to help us diagnose the effect of plasma buildups that happen within the targets, on the ICF targets at bang time. And we believe that this buildup is kind of influencing the yields that we're getting, but we lack the diagnostic capabilities. This is a schematic of the system. It's another large-scale system that requires a separate new beamline, similar to ARC. We're also focused on increasing the amount of power and energy that we're getting from NIF. Its current baseline is 1.8 megajoules and 500 terawatts. We haven't set a goal yet for where we want to increase it to, but we do need to restore our precision diagnostic suite of tools, which was a large-scale controls effort in order to determine where the new baseline energy is that we're shooting for. And then our shot rate improvements that we did was really just the first phase. Over the next year or two, we're also investing in a phase 2 to further reduce the shot-to-shot time by another 30%. And this is a bit more investment in engineering as well as software changes for further more radical automation. So in conclusion, the control system is critical for effective and efficient use as we advance or study our various primary mission spaces. The shot rate improvements that we previously spoke about were all completed and the goals were exceeded while maintaining a flat funding level. And then we've proven already this year that the improvements are sustainable for going forward. whilst we're still continuing to add many new laser and diagnostic capabilities to further expand the scientific value that we're extracting from the facility. And then we also recognize that sustainability of the control system is important, and so we do invest in modernization in order to adequately support the facility for the next 20 years. Thank you for your consideration.
Thank you for the speaker. The time is limited. One quick questions. Okay. Andy. Okay.
Andy?
In San Francisco 4 years ago, I think your director spoke about producing energy with NIF. What happened to that project?
Producing?
Energy, using it as an energy source. He was going to do fusion.
So that was the ICF mission. I mean, one of the mission spaces that we are trying to explore is using fusion as an alternative, safer nuclear power source. I mean, it's science, it's R&D. I mean, we are trying to finesse the parameters to try and squeeze as much out. I mean, we're already into the kind of burning plasma kind of regions of ignition, where we actually are able to extract more energy out than we put onto target. And some really significant near-term goals that we've achieved recently are very positive. But it's a very difficult subject to predict, but it still is one of our very key primary missions. So.
Okay, thank you.
Thank you.